So structure and isomerization in coordination compounds. Isomers are very common in coordination compounds. And we can divide these into two broad categories, structural isomers and stereoisomers. So a structural isomer, a pair of structural isomers will have the same atoms, but they're going to have different connectivities. So they'll be connected in different ways. In a pair of stereoisomers, the atoms are going to be connected in the same way, but they have different spatial arrangements. So without looking at their three-dimensional shape, you would not be able to tell that they aren't exactly the same molecule. And then each of these is subdivided further. They're subcategories. So first we'll look at the structural isomers. So coordination isomers occur when you have the coordinated ligand being exchanged with an uncoordinated counter ion. So the example here we have cobalt, and its ligands are 5 ammonia molecules and 1 bromide ion. And the counter ion is a chloride ion. So if we exchange the bromide and the chloride and have the chloride now be coordinated and the bromide be the counter ion, this is a structural isomer because the things are connected differently. And it's different because of what is coordinated and what isn't. Does that make sense? This means yes. This means no. Because I'll explain it more if you want, but you good? Okay. Thank you. Okay, linkage isomers. Here we have the same ligands, but some of the ligands are hooked up differently. Some ligands can coordinate with using more than one atom. So an example of this is the nitrite ion. So this can coordinate with the nitrogen ion's lone pair, doing the coordinate covalent bond with the metal ion, or with one of the oxygens, because the oxygens have lone pairs too. And so it can be attached by the nitrogen or by the oxygen. The chemical formula would be the same, but it's combined differently, and it's not exactly the same molecule, so they are isomers. These have separate names. If the nitrogen is attached, it's called nitro, and if the oxygen is attached, it's called nitrito. Aren't you glad you don't have an in-class exam on this, where you'd have to memorize all these things? So here we have two linkage isomers. We have pentaamine nitrocobalt-3 and pentaamine nitrito cobalt-3. So the nitro isomer is more of a yellowish orange, and the nitrito isomer has a darker color. And the difference here is how that nitrite ion is attached. Here it's attached by an oxygen, and here it's attached by the nitrogen. Any questions? So here are 4 of the ligands that are capable of the linkage isomerism. Stereoisomers have different arrangements in space. So one category of stereoisomers is a geometric isomer. So here we have the ligands bonding to the metal in different spatial arrangements. So here we have 2 examples. These are called Cis-Trans Isomers. Cis means same side, and trans means opposite sides. So you think of the Trans-American Railroad, right? It goes across, right? And cis, if you like your sister, hopefully you're on the same side of a fight. So cis is same side. So here we have platinum has got 2 chlorine ligands and 2 ammonia ligands. And the ammonia ligands are on the same side of this square planar shape. Here, the ammonia ligands are on opposite side, so that's trans. And they don't just move around and rearrange without breaking and reforming the coordinate covalent bond. So these are 2 separate compounds. Any questions? This can also happen in octahedral complexes where you've got the metal with 4 of one ligand and 2 of another. So here you can have the 2 chlorines next to each other. This would be the cis isomer, or here they're opposite each other. In a tetrahedral complex, you can't have cis-trans isomers because all 4 of the corners are adjacent to the other 3, right? So you can't have together and across. Then we have Fac-Mer Isomerism. And this happens in octahedral complexes where you've got 3 ligands of one kind and 3 ligands of another kind. And so this has to do with the positions equatorial and so this is the equatorial positions and these are the axial positions. So that's not the best explanation. Let's go with this one. So the facial isomer or the Fac isomer, we've got the 3 chlorine ligands on one side, and so they make a triangle. One of the faces of the octahedron is composed of 3 of the same ligand. In this isomer, you would make a face by using this one and that one. You can't draw a triangle face using the 3 chlorines or the 3 ammonias. So this is called meridian. So here we have these around the meridian. I really think they should have tipped it sideways because these are in the equatorial positions. They form an arc around the middle of the, what is that? Complex ion, sorry. Any questions? Some of these things you almost need a model kit or some marshmallows and toothpicks or Tinker Toys or something so that you can like make these and play with them because it's a little hard to look at. Okay, so draw the structures and label the type of all the isomers of each complex ion. So here we've got chromium, and it's got 3 water molecules and 3 chloride ions. So there's a total of 6 ligands. One thing that can make drawing these a lot easier is just to use letters. So we'll say that A is going to stand in for water, and B is going to stand in for chloride, so that we don't have to draw as many letters. So we've got our chromium in the middle, and we've got 6 ligands, so this is an octahedral. So this is the vertical axis, these are the axial positions, and then these are the equatorial positions. So this is a little bit like a little girl wearing a tutu, and her tutu is sticking straight out. So then we need to put 3 A's and 3 B's on here. So I could put A, B, B, B. So that's one way to do it. Now the tricky thing about this is that you can draw the same isotope and think it's different if you don't know what you're doing. So if I did this, is that the same or different than the first one? That's the same thing. That's the Fac isomer, the facial isomer, because these 3 A's form a triangle, one of the faces on the octahedron. And they also form a triangle here. And so this has just been rotated. It's exactly the same thing. So we have to to switch something around. So if I switch A and B there. Now the three A's are around the equator. They're in the meridian position. They're in the 2-2, if you will. And the B's are in the axial positions. And so this is the meridian, or the Mer isomer, and this is the Fac isomer. Any questions? Oops. So this is Mer, Cr H2O3 Cl3 plus, and that one's fast, the same. Any questions? Okay, let's do this one. So here we've got 2 ammonias, 2 chlorides, and what does ox mean? Oxalate. So again, let's abbreviate things here. The take-home exam wants you to abbreviate when you do the drawings. Oops. And then chlorine equals chlorine. That's helpful. Oh, good grief. So how many ligands do we have here? 5 ligands, right? So put the cobalt in here. What shape does 5 take? Trigonal bipyramid. Oh yeah, that's right. So this, again, is like a little girl with a tutu, but her tutu is not as full. It only has 3 ligands in it instead of 4. So we got 2 chlorines, 2 ammonias, and an oxalate. Well, we could put the ammonias opposite each other and put the chlorines and the oxalate around there. What if we put the chlorides opposite each other? Is that different? Yeah, it is. Here, I'm just going to call them by the letters. The A's are opposite each other. They have a 180-degree angle. Here, the A's have a 120-degree angle, and the B's have a 180. So they're in different positions. Could we do something still different?
Did you sub the C into an axis and then put a B with it or put an A with it?
Yeah, so we could put the C up here and maybe just put the B down there. A, B. Running out of space because I made that one too big. And if we put an A down here and a C up there, and now, are these two different? Yeah, they are. They are. Because here, B and C are in the axial positions, and here, A and C are in the axial positions. If this was an octahedral complex, they would be the same because you could just rotate it and it'd be the same. But these are distinct. So there's four different ones. The labeling of those, gets to be a little complicated. These were pretty easy. I think that these two would most likely be called a trans isomers, but you'd still have to distinguish between them because they're not the same. And these would be cis isomers. But again, they're slightly different, and so they would need unique names, and your book doesn't go into that, so I'm not going to either. Another type of stereoisomer is an optical isomer. You'll hear a lot about this in organic chemistry. So optical isomers are non-superimposable mirror images of each other. At the end of your arms, you have two optical isomers called hands, right? So your hands are mirror images of each other, right? You hold your hand up to a mirror and it looks like your other hand is in the mirror, right? And yet you can't superimpose them on each other. That's why there's a left glove and a right glove, right? Because if you try to do it backwards, the thumb's pointing in the wrong direction. I mean, you can try, but you cannot superimpose. You can get four of the fingers on top of each other, but then your thumbs are sticking out, right? You can't superimpose them. So looking at molecules, here we have this molecule, and this is a, I bet that's what they wanted us to do. We're going to ignore it. I think oxalate was a bidentate ligand, and we were supposed to do this, but we're going to ignore that. These are bidentate ligands that are connecting here, so they're attached in two places. So this one and that one are mirror images of each other. But if you take the mirror image and try to twist it around and put it on that one to superimpose it, you can't. They're called optical isomers because they rotate polarized light. So it has an optical activity, and that's something that can actually be measured. The two isomers are called enantiomers. So enantiomers are two optical isomers. And we use the word chiral to describe things that exhibit optical isomerism. So we'll see this in octahedral complex ions. It's possible in tetrahedral complexes, but only if you have four different ligands. That's what happens in organic chemistry with carbon. If you have four different things attached to the carbon, you get a chiral molecule, and it can either be right-handed or left-handed. So this one's asking us, determine whether the Fac-Mer isomers of CrH2O3, are optically active. So optically active means that they are optical isomers. They're mirror images, but not superimposable. Whoops, that's what I want. So, good grief. So we did these ones earlier. So if we look at the Fac isomer, we're going to have A, and B. Now, the mirror image of that so here's the mirror. If this one looks in the mirror, it would see something that looks like that. are those superimposable? Can you take this one and just rotate it in space and make it look exactly like this one? Yeah. If you just take this one and rotate it 180 degrees, it becomes this one. These are not optically active. So let's look at the other one. So, no, that's not what I wanted to do. Put the A's, good grief, A's around the middle, meridian, and the B's in the other places. There's the mirror. A, B, B, A, B. So this is the Mer isomer where we have 3 of the same kind around the meridian. And then this would be the mirror image of it. And can you rotate this one and have it look just like this one? Yes, you can. So leave the B's where they are and just rotate this around 90 degrees, and you'll have the same thing. So neither of these are optically active. Questions?